Let's move to the next talk of this afternoon. The next speaker is Caio Ribeiro. He'll be talking about quantum back reaction in Bose-Einstein condensates.
Thank you. Can you hear me? Okay. Okay. First of all, it is a great honor for me to be participating in this event in honor to Professor Dodonov. And I'll take a step back with respect to the previous in-depth presentation by Professor Fischer. And I would like to introduce the concept of quantum back reaction in Bose-Einstein condensates, assuming a more pedagogical and accessible manner, okay? Also, I'm not an expert in many-body theory or in Bose-Einstein condensates, so it is better for us to keep at the introductory level, okay? Okay, so let's start with some general aspects regarding these systems. As a field theory, as in any field theory, we should start from the very beginning, and the very beginning is for us to assume a Lagrangian description or an action for our theory. So, what do we want to do? We have a box, and this box is full of bosons, okay? And we want to study these bosons inside this box. So we can assume that this gas that is inside our box is a non-relativistic gas, and we can take for it, for instance, that non-relativistic action. Okay, our variable is this psi function, which is a complex function. Okay, v, the parameter v, the function v that is appearing there in our action is here to model the walls of our box. So a box trap or a harmonic trap or anything that you want to do. Just put it that and solve the field equations. This theory described by that action has a global U1 symmetry. It is invariant under that global phase transformation there. And we know from classical mechanics that being that the case, there is an actual symmetry on the space of classical solutions. The symmetry is the U1 symmetry. And in mathematical terms, it's just a continuity equation. And because of this symmetry, we actually gain an interpretation. There is a quantity, which I'm calling ρ, which has an interpretation of a particle density. So locally, this function measures how many particles per unit volume we do have inside this box, okay? And this J here is the usual particle current. And of course, if we integrate over all this space, the particle density, we have the total number of atoms inside our box, okay? So this is just a starting point for us. As usual, the canonically conjugated momentum is defined by taking the derivative of the Lagrangian with respect to the time variation of our variable. So in this case, it's just this function here. And the Euler-Lagrange equation, everybody knows it, is the Schrödinger equation in this case. And let's solve this for a very particular case in which our box is modeled by a harmonic trap or something like that. It means that we just have a harmonic potential here. When we do that, we can actually solve that exactly. And our wave function is written in a rather general form by spending a complete set of field modes. Okay, so this is just Fourier analysis of our variable. And this omega n here, this n is a three-dimensional vector with natural entries, okay? And these omega n's, they are just this quantity that is appearing here. Okay. The advantage of doing that, of using Fourier decomposition for writing the wave function, is that if we now calculate the particle number, the total number of particles in our gas, we just integrate the density, and we get this very well-known expression. So for each n, for each vector n, this pair of complex numbers, when we take the absolute square of it, gives us some contribution to the total number of particles. More than that, we also have the notion of energy, or Hamiltonian, which is a Legendre transform of our Lagrangian, and it has the usual form as well. Okay, so very general aspects of it. And what we do about that? Well, we want to study the quantum part of the theory. So as usual, we start with that classical field theory, and then we just put hats over all the quantities, the observable quantities, okay? So this is imposed, this is a postulate, and it is equivalent to the usual harmonic oscillator canonical commutation relation. So for each vector n, we do have a harmonic oscillator. So instead of treating a single harmonic oscillator, as in yesterday, we will treat an infinite number of them. That's the only difference. Okay. We want to do thermodynamics, equilibrium conditions. So what we do, we take the grand canonical ensemble. All of this is just following the natural recipe. And we take averages of a given observable. So we have definitions here, and the temperature is just the 1 over beta, as usual. Mu is the chemical potential that measures, it is equivalent to either work with the total particle number or the chemical potential. And the interesting part is that now, after we quantize the theory, the number of particles in our system is just the average of the number of Pareto, which inside the formalism of statistical physics assumes this very nice form. And here we see immediately the Bose statistics. Of course, we are treating bosons here. And it is convenient to separate off the number of particles in the ground state. The state with all of n entries taken 0, which is a state with the smaller energy in our system. Okay. We'll define that Bose-Einstein condensation occurs when the number of particles in that fundamental state is comparable to the total number of particles in our system. Okay, so this ratio here should be comparable to 1. And for this particular very idealized model of an ideal Bose gas, this happens when the chemical potential is comparable to the energy, to the frequency of the ground state. Okay? When that's the case, we can actually solve by taking the limit of an infinite number of particles. We can solve these equations, and we get that nice and well-known formula in the literature that plots the number of particles in the ground state with respect to n as a function of temperature. And here we have a parameter, which is a critical temperature, which is given by this quantity here in terms of our system, which is given by the trapping potential details and the number of particles, of course. Typical values, as Professor Fischer already started to talk about. Typical values for the critical temperature, 60 nanokelvins. So it's a very, very small temperature, and that's for 1,000 particles and trapping frequency of 100 hertz. Yeah, I will come to that. But the point is that they are similar. So there's already an indication. Yeah. So here I'm showing a now old experimental picture showing the good agreement of that theoretical prediction with the experimental data. Okay, that's it. Now let's talk a little bit about the condensate state. What is a condensate from the point of view of quantum mechanics? Suppose that we are saying that the ground state of the theory is given by this vector here, and we want to study the limit where the particle number, the total number of bosons is very high and temperature is tending to 0. Okay? When that's the case, because we do have a density interpretation to act with A in this state has a meaning of destructing a boson. That, of course, is not true for any field theory. For photon, that's not the case. But here, if we act with this destruction operator on the ground state, we remove a boson for the theory from our box. But because the number of bosons is so big, it's tending to infinity, this vector is almost the same as the original vector. Okay, assuming some sort of continuity in this parameter. Being that the case, we immediately recognize that we do have a coherent state. Aha. So somehow a coherent state description appeared from this very general idealized boson gas. When that's the case, the action of this operator in the ground state is the same as multiplying by this number here. And it is convenient to separate the wave function in the dominant part plus a small, in some sense, contribution. Okay, this is very important for us. Now comes the real interesting question. How do we justify this limit taking an infinite number of particles and instead assuming that these particles do not interact, that we do have an ideal gas? Well, that's obviously wrong. We cannot do that. And we must consider somehow interactions. Okay, so here we do have interaction energy written in a very general way. No? A 2-point interaction energy, which might be a dipolar interaction or like in Cooper pairs, interacting and so on. So the sky is the limit here, literally. And typical values of these atoms in an experiment are range between 1,000 and 5,000. And here I pose a question: why? Because we obtained our results for in the thermodynamic limit for each n is formally going to infinity, but experimentally that's far from being true. Okay. So if we assume that our gas is very dilute, we can use something called the S-wave approximation, which amounts to take the interaction energy proportional to a delta function. In this case, we say that we have a local condensate, a local interacting gas, and this G is proportional to the scattering length, but I won't enter the details here. They are not important for us. Being that the case, the field equation now becomes the well-known Gross-Ptolemy equation. Okay, so we do have the usual Schrödinger part, the linear Schrödinger part that we started with, but now we do have a non-linearity here, which tends to give the very nice results of these condensates. And also for the back reaction scheme that we are going to discuss, it is very, very instructive to use the Madelung representation, which amounts to work with the absolute value of psi and its phase instead of the complex function. And if we take this resolution and put it back in the Gross-Ptolemy equation, we do get the formulas that Professor Fischer showed you. The continuity equation and the Euler equation with the quantum pressure here modeling the effects of the condensate. Okay, so this supposedly both these equations are equivalent. Here V, which is the gradient of the phase, is just the velocity, the local velocity of the fluid. Okay, so that's it for the general aspects. Now we start with Bogoliubov theory. The problem is we do have a general gas, a general condensate, and we want to do something with it. We want to model it and extract information from it. How we do that? Okay, we start from the Heisenberg equation of motion. We know already that. And we can, assuming that expansion that I showed you before, we can actually perform an expansion. We assume that the wave function has a dominant part plus a small perturbation, which is small in some sense. That will be defined later on. We do that because this is a C number, it's just a number. The commutation relation for this operator now is written in terms of our perturbation and assumes the usual form. And the perturbation, if we linearize Gross-Plejevsky equation, or even better, the Heisenberg equation, we obtain the Bogoliubov-de equation. So the perturbations at this level, they follow a different equation from the condensate part. When we do that, the particle density now gets a small contribution over this background density, and the same for the particle current. Okay, so here it is separated. We do have the background current plus the perturbation. This delta rho is called the quantum depletion, and it models the number of particles that actually got out of the condensate that are not in the condensate phase. And this phonon flux is, as the name says, the flux of perturbations inside, over this condensate background. Just a note, quantum depletion exists even at zero temperature. For liquid helium, for instance, we do have this ratio here. And very important for our back reaction scheme, this expansion, Bogoliubov expansion, actually breaks the U1 symmetry. We do not have the number conservation anymore. Okay, and that's very crucial because you do have a theory that if you consider only that, the number of particles is actually increasing with time, and that cannot be the case in our box, a closed system. Quantum depletion was measured very recently by Hatzibabich. They confirmed this 70 years old prediction to show to you how easy it is to probe quantum depletion in an actual experiment. And okay, let's start to gravitate towards the back reaction now. A crucial aspect of back reaction is called phase diffusion. What is phase diffusion? It is, we can also write the wave operator like so, using this quantum Madelung representation. If we do that, we can identify actually a small phase operator to our description. And it turns out that for interacting condensates, this phase the variance of the phase actually diverges with t squared when there are interactions. That's bad because vacuum fluctuations, they naturally tend to destroy the condensate. As the condensate is formed, it starts to degrading until you don't have a condensate anymore. And that's spontaneous, any spontaneous process, okay? It was published in this nice paper here. And there are also other different type of theories for which this U1 symmetry is preserved throughout the expansion. Here I have perhaps the most important paper about that by Van Castan. But even in this type of theories, you can even show that if you have some sort of Poissonian distribution to the ground state, you still have phase diffusion. So it comes to the definition of what is a condensate. It depends on the guy that is actually doing the calculation. What is a condensate? For me, I agree with this guy right here. A condensate is a coherent light state, which is therefore undergoing phase diffusion. That's what is a condensate for me. So let's talk about quantum back reaction finally. We do have the spontaneous breakdown of number conservation symmetry. We do have the spontaneous breakdown of time translation symmetry, because if the condensate is ceasing to exist in a spontaneous manner, it is hard for you to actually identify in which part of the process the condensate is. And of course, as particles leave the condensate, there are still interactions between these particles and the condensate. Okay, so now we come to the main question: is the condensate still ruled by the Euler equations? Well, that might not be the case, and we must consider on this evolution the quantum corrections. How to model that then? Well, first of all, this back reaction model should be U1 symmetric. We must have particle number conservation. And the back reaction is meaningful as long as Bogoliubov theory makes sense. That is, back reaction should be something small acting on the main part of the system. Otherwise, this is not back reaction anymore. So let's follow this back reaction scheme in which we actually expand the wave function in a dominant part plus the quantum fluctuations plus the smaller order corrections. So this phi 0 is of order n to the square root of n. This chi is of order 1, and this zeta is of order n to minus 1/2. When we do that, at dominant order, we do get the usual Gross-Plevsky equation. At order 1, we do get the Bogoliubov-de Gennes equation. And finally, at order n to minus 1/2, we do have this inhomogeneous Bogoliubov-de Gennes-like equation for the zeta, which has some source terms now, depending on the quantum fluctuations and, of course, the dominant part of the expansion. Accordingly, the full particle density now is the dominant part plus quantum depletion plus some correction here, and these corrections, this whole zeta, they have the same order as the quantum depletion. So as usual, this is quantum depletion, J chi is the phonon flux, and we do have these extra corrections. What is important about that is that we do have number of conservation up to order 1. So our back reaction scheme will follow this idea, this expansion. More than that, is the condensate evolution Eulerian in some sense? Meaning, is the time derivative of J given by the Euler equation, the usual Euler equation? Well, if the condensate evolution, if the condensate was not subject to these quantum corrections, this would be the case, as we just saw. But now we should expect some quantum corrections there, okay? And that's the only hard equation that I will present to you guys. This is the quantum force to order 1, okay? This is very compact expression. And you see this quantum force density, it depends only on the quantum fluctuations. So phonon flux, quantum depletion, this is particle number fluctuation, and the dominant parts of the theory. Okay, so to finish this back reaction idea, I will present to you some nuances of the other nuance of this back reaction idea. First of all, to start back reaction then in the system, we must solve this system of equations, which is a first order system of equation in time. So you do have to specify both the system density and the system flux as some initial time for you to have an actual evolution, a consistent evolution. But there is a major problem here, which is we do have phase diffusion. And if we do have phase diffusion, it means that from a field theoretical perspective, that you have actually an uncountable many equivalent ways of choosing a quasi-particle vacuum. You cannot know for sure in a given experimental realization which vacuum you do have in your theory. So you might wonder, okay, so this back reaction scheme serves to no purpose because you cannot actually use it to make experimental predictions. Well, there is a way off, and the experimentalists, they do know that. You should start with a very weakly interacting condensate, because if that's the case, there is no phase diffusion. And then you perform some quantum quench to a finite interaction strength. By doing that, the vacuum state of the theory is well defined throughout the evolution. So there is no indeterminacy. And here I'm showing to you, because it is very hard to solve, so we do the easy thing, which is construct an exact solution to the back reaction problem. This is just a homogeneous density condensate, which is realizable, a finite size, of course, which is realizable in state-of-the-art laboratories. For instance, Hatzi-Babbage can do that. So it's just a very small homogeneous condensate, starting from a non-interacting regime, and then you turn on the interactions. When you do that, this is what you get for the particle density as time passes. So this is the particle density over the background, the homogeneous density. So you have the accumulation of particles at some places and the depletion of particles in other places. And this is the correction to the condensate current. The condensate actually starts to move to account for the atom number conservation in this system. Okay, so this is just quantum depletion, but this has some very deep experimental problems to it, which I won't enter the merit here. And just to finish, some perspective, and our perspective at least is linked to analog Hawking radiation. Okay, we do have to probe Hawking radiation. As Professor Fisher told us, this is very bad, very hard, essentially impossible for a real black hole, because we do have the cosmic microwave background radiation, which is almost 3 kelvins, and the Hawking temperature is negligibly small. And then who came and revived this idea, this very old idea of, okay, let's do that in the laboratory. The idea, we do have a flowing fluid, and we have a notion of an effective event horizon which separates a supersonic from a subsonic region. In general, for our case, we build an exact solution to study the back reaction model. Our goal is to study the back reaction model, to apply the back reaction model to this system. So in order to do that, we must have a black hole for which we can actually calculate quantum depletion and quantum flux and phonon flux. And we did find an exact solution for that. This is an atom laser. So it's just a condensate flowing like that with a coherent source here and a coherent drain at the other end. And we tune the local Mach number in such a way as to have an event horizon somewhere in the middle of the atom laser. When we do that, we can actually build an exact solution for the quantum depletion in the system. So we start these black curves. Let's pay attention to the lower panel. This black curve is just the initial stationary atom laser. So this is quantum depletion in that configuration. And then we turn on we perform a quench in the downstream Mach number to form a black hole. So Mach number is smaller than 1 subsonic region, Mach number higher than 1 supersonic region. When we do that, we see that the quantum depletion starts to develop, and we get this characteristic profile indicating that the Hawking radiation is actually, you can actually see the Hawking radiation by analyzing the depletion profile. Our idea is that with this exact solution, we can somehow apply our back reaction scheme. But I guarantee to you that although we can build a formally exact solution for it, it is very hard to visualize it at least in my laptop. So, but I'm not an expert in it. But that's the general idea. Thank you.